All right, guys. So combinatorial analysis first lecture. First is to learn how do we count. So I flip a coin, and with a flip of the coin, there are only two possibilities. I either get heads or tails. Let's say that the possibility of the coin landing on the side is something that we ignore. Okay. And so we have only two outcomes, very easy to count. Second possibility, we now, our experiment consists in tossing a coin and a die, okay? The outcomes that are possible clearly are, first outcome is heads, and then second is you get one on the die, or heads and two on the die, or all the way to heads and six on the die. All right, so this is the outcomes that resulted in a coin coming up heads and the die coming at any number. There are six possibilities. And the other possibility, I write it as another row. It's tail and then the die roll. So far, good? So in general, we want to know if we have two experiments, experiment 1 and experiment 2. And experiment 1 has m outcomes and experiment 2 has n outcomes. How do we count all the possibilities combined, right? So for each outcome in experiment 1, there are n outcomes independently. Okay, it doesn't matter what experiment 1 produced as an outcome, there will be n outcomes for experiment 2. Make sense? So for example, with the coin, there are 2 outcomes for experiment 1, and the die will produce 6 outcomes for experiment 2. Okay, and doesn't matter what the coin produces for outcome, the die will produce 6 outcomes, no matter what. Yes. So how many possibilities are there to count it all together? So how can we do this? In general, if experiment 1 has m outcomes and experiment 2 has n outcomes, I can write it in a matrix, right? So I represent outcome 1, that would be the first row. Outcome 2 of this experiment 1 is second row. Outcome m on the first experiment will be the mth row. You with me, guys? So what we generate, and then the columns will represent outcomes of experiment 2. So what I have generated is a rectangle, right? I can see how to count it, right? We have a rectangle that has m rows and n columns. Good. So altogether, the number will be by just you just can count it. Just m rows times the columns is just m times n. So nobody is confused at the moment. Am I right? Good. So here is immediately a very very simple question. So suppose we have 10 women, and each woman has exactly 3 children. And what we're going to do, we're going to pick one woman and one of her children and designate them as woman and child of the year. So how many possibilities are there, right? And what you have to learn is, okay, it's going to be very easy right now. It's going to be very, very difficult very soon, okay? You rather have to develop a very logical way of counting. So how are you going to do this? So naturally, I can assign to each woman a tag. So she's holding a tag, woman 1, woman 2, woman, all the way to woman 10, yes? And each of her children will be also wearing tags, 1 through 3, let's say, okay? So then I have a pairing, right? I can describe the situation as a vector. So I can say, for example, the outcome came to be 2, 3, which means woman number 2 was picked as the best mother, and child number 3 was picked as the best child. You can decide how you assign numbers to children. Maybe you assign the numbers to women based on their age, their birthday, their name, and to children based on whatever you like, right? But you have to have a clear picture of how you assign the numbers, okay? So then you can clearly see outcome 2, 3, what it represents, right? And outcome 1, 3 represents a very different situation. The 3 in the second coordinate refers to a different child, correct? 1 and 2, sorry, 1 and 3, or 2 and 3 refer to, the 3 refers in each case to a different child. Do you agree? So that goes to show you that perhaps the results of experiment 2 will depend on what happens in experiment 1, but what matters is that the number of outcomes in experiment 2 per each outcome of experiment 1 remains the same. So notice here we have 10 women and each has 3 children, okay? That's when the basic principle of counting will work, what I just showed over there, okay? So how many possibilities are there? Here is the breakthrough. This is what we did. Here is a woman labeled 1 through 10, each of her child labeled 1 through 3, okay? And I want you to be bureaucratic, okay? If you read Kafka, if you know who is Kafka, so you have to be that bureaucratic in this class. You want documents, okay? You want to document every single thing that you count. And the document I imagine in my head is something like this, okay? Where the first number is 1 through 10, and the second number is 1 through 3. Oh, the second number cannot be higher than 3 in this situation, okay? So here, this document is filled in with the number 4 and 2. Good? Four and 2, which means mother number 4 and her corresponding child number 2 were selected. If I change 4 to 5 and I keep the 2, that refers to a different child again. Make sense? Now, because I have this box, this now is experiment 1. This box has 10 possibilities of being filled, and the second box has 3 possibilities of being filled. It's 10 times 3. Are you with me, guys? You look like a very sad and quiet bunch, guys, and that's just the first day, right? That's why my first lecture for calculus is about our situation. Why is it that we are so separated? You know, when this entire thing began last semester, I was rather perplexed, and I said, if that's where we are, let's have office hours at the cemetery. And some people actually wanted to come. So you see, that's with these boxes, you would remember what happens. Here is experiment 1, 10 possibilities, experiment 2, 3 possibilities, 10 times 3, because I can arrange, I can have here 10 rows and 3 columns. 10 rows by 3 columns, it's a rectangle, which is 10 by 3, which is 30. Okay, and now let's consider how do we figure out, and be very precise about it, the generalized principle of counting, the basic principle of counting, but where you have more than one experiment performed. So what this means is that we have one situation in which we have 1 through n1 outcomes, independently of what happened here. The number of outcomes that are possible in experiment 2 would be 1 through n2, and so on, up to some experiment r, where the number of outcomes is 1 through n sub r. So my question is, let's see, first of all, you might already know the answer. What would be the total number of possible outcomes here? Valeria, do you want to say something?
10 to the third.
Well, because we don't necessarily have 10 here, there are no numbers listed here, right? It's just abstract 1 through n1, then 1 through n2, then all the way to 1 through nr. So we're trying to come up with a general formula, right? If it were 10, 10, 10, and there were only 3, that would be 10 to the third, you're right. But this just means in general, right? In general.
And multiply by r?
You see, look at the labels. They don't have the same number. So here it's 10 and here it's 3. So in general, this might be 10, next might be 30, the next might be 5, the next might be 7. Notice dot, 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 it's 2, 3, all the way to r. So what might any of you imagine is the number of outcomes, that list outcomes for experiment 1, then experiment 2, all the way to experiment r?
Would it just be n1 times n2 times all the way to nr?
It would be, precisely. But even if you see that this is the case, the question is, how do you truly notice that, okay? So I would propose that you think about it in induction, okay? So I can take experiment 1 and experiment 2 and think of the 2 as a super experiment, right? So experiment 1 contains 1 through n1 outcomes. And again, Valeria and everybody else, I'm just speaking abstractly, right? If it bothers you, the N1 and 2, it's just really imagine that this has some number of outcomes. Let's say 5. This one has 10 outcomes. The next has 17 outcomes, right? This is just to try to describe all possibilities for each experiment separately. Okay. So in general, experiment 1 has N1 outcomes. Experiment 2 has N2 outcomes. Altogether, by basic principle of counting, I can just see it would be containing, let's say if I put experiment 1 as the rows, I would have N1 rows and N2 columns. Do you all understand? So I picture this. I picture this structure, okay, for those experiments. That's what we did in general. Instead of M and N, I have N1 and N2. So I will have N1 rows and N2 columns. Yes, guys? If it's all, guys, if you think it's all very simple, trust me, right? You just do not know how bad it gets, okay? I am trying to train you to think bureaucratically, right? If you ever read the Kafka's book, Das Schloss, the castle, then that is specifically what we have to think. I made myself many errors until I figured out how to avoid such errors. So what it means now is that I can think of experiment 1 and experiment 2 together as a super experiment consisting of N1 times N2 possibilities. Do you understand? Yes or no, guys? Good. And the others I don't hear or don't see, guys, I do hope you participate, right? Yes, somebody came here. Okay. I do hope you do your best, right, under the circumstances. Okay. So it's N1 times N2. Now I collapse them into one. I can then collapse them into a super experiment, right? I now have, instead of 2 experiments, I have 1, but with more outcomes. Now I can take experiment 3 and I can collapse them by basic principle of counting again. I can have N1 and 2 times N3. And continuing in this fashion, I see that the result, as Shotaro just mentioned, is N1 times N2 all the way to N sub R. You understand? I multiply all the possibilities. Or if you have a very good sense of dimension, this is an R-dimensional rectangle, right? But I'm not sure how many dimensions can you picture. You might be able to picture 3. All right, so here is, and I want you to think about the documentation that will make this work. So we need to construct a license plate. The license plate is to have 7 letters. I mean, actually, 3 places are reserved for letters, and the remaining 4 places are reserved for numbers 0 through 9. Okay, so the license plate begins with 3 letters, 3 English letters, followed by any digits, any 4 digits. The question is, how many license plates are possible? Think about it and either well, text to me, or and I will look at what your answers are, or
Professor, wouldn't you do like, wait, how many letters in the alphabet again? 26, 26?
26 letters in the alphabet.
Right, wouldn't you do 26 times, well, 26 cube times 4, wait, how many? 10 cube? 10.
Yeah, you
10 to the 4th, right?
Well, 9 if you use digits 1 through 9, then you're right. It's 9.
It's 10.
But it's 10 if we're using 0, right? So assuming we're going to use 0.
Right.
Yes. Okay. So what matters is, again, guys, this is still a very simple question, right? And you don't bother with multiplication, etc. I just want you to understand the form of the argument. Okay, understand the form of the argument. And what it does is this, right? So we have here is our document. In the document, First code is first experiment. First box is first experiment. Second box is second experiment. Third box is third experiment, all the way to the seventh. So the first experiment is to select a letter. There are 1 all the way to 26 letters, right? So first letter is A, second letter is B, the 26th letter is Z, I suppose, right? So there are going to be 26 possibilities here. 26 possibilities here, 26 possibilities here, right? So that would be 26 to the power of 3 possibilities. So 1, 2, 3 produce a super experiment of the form 26 to the power of 3. Good?
Yeah.
And what about the remaining places? The remaining places are each 10 possibilities. 10, 10, 10. How many 10? They're only 7 minus 4 plus 1, which would be 7 minus 3, or 4 possibilities. So it's 10 to the 4. At the slightest, guys, at the slightest misunderstanding, please don't be afraid to talk to me. If you are for some reason are shy in front of other students, you can talk to me during office hours, let's say after class. Good? Okay.
What about some restrictions with repetition?
Well, we will, this is the very, very basic thing. And we're just talking about the basic principle of counting. And even as the questions will get extremely difficult, most of it is just an application of the basic principle of counting. Okay? Okay, so wait, I mean, this is just my basic point right now is the boxes. I want you to think this way, okay? You will see when it will come to be very important. Here is another question. How many functions defined on n points? You understand what n points are? Just so a function is going to map 1, and then digit 2, then digit 3, n numbers, it's going to map them somewhere. And each number is either mapped to 0 or to 1. How many such functions are possible? Think about it.
Julian, yeah.
Erica, thank you so very much for the answer. It is 2 to the n. Now, I want you to all understand why it's 2 to the n. So let's say if you don't like the number n for a moment, right? If you think, let's say concretely, imagine that n is 7. Imagine that what we have is this, those boxes I drew over here, right? So if n were 7, then the first input, 1, where can it go? Either to 0 or 1. So this box can either be written, inside of this box, you can write either 0 or you can write 1. In this box, you can write either 0 or 1. And in all the others, so how many possibilities? It's 2 times 2. It's 2 squared, 2 cubed, 2 to the 4th, all the way to 2 to the 7th. So in general, if there are n boxes, n just means, I don't know what's the number, it's just some number, right? Maybe 1 million, I don't know. That would be 2 to the power of this number. Are you with me, guys, all of you?
Yeah.
All of you with me?
Yes.
Right,
Yeah.
guys, that's good. And you, Melissa, are you with me? Maybe not. Ah, yes, Melissa is with me. Great. And you understood it, Melissa, yes? Sorry, I pick on you. But, you know, guys, I try to drag here people from all sorts of places. So this is the boxes in general, 1 through n, so it's 2 to the n, okay? And now let's consider permutations, okay? That's still pretty simple. So permutations work like this, right? So we have n students, and the n students are going to be put linearly against a wall. So that basically, you know, you can see which student is leftmost, which is next, which is next. They are all against the wall, and then you're going to take a photograph of them. Okay, so I would say what the question is, of course, is how many possible photographs can I take? Where what matters in the photograph is who stands where. You understand? The photograph consists of the same background. Let's say the background is black, so you don't think the photographs are distinguishable. And what you see is the individuals, right? So let's say here is one person, here is second person, or if it's like this, you see a difference, you see? This photograph is different from this photograph. And you have in general n individuals. how many possible photographs can be taken? Yes, Kazi, correct. But also, I hope we will go through it together, that you have a very, very clear picture of why that's the case. That's very important. Are you waiting for me, guys, or you're thinking? Well, let me know, guys, text when you think you're ready, and I will go on with the answer. Or if you want to think more, write, please, that you want to think a little longer. Okay. Thank you. Okay, I will continue. So that will come in handy later on. First of all, I have this philosophy that two objects that occupy different places in space at the same time are definitely different objects. They're not the same, even if they look alike. You will see that that matters soon. Okay. So what happens here is, in this experiment, is I can imagine that each of those people either wear a tag or have swallowed a number. Inside of them, there is a number that makes them distinguishable. I think of it because I have hard time distinguishing between certain students. I then imagine that each of them has swallowed an integer. Okay, so either the integer is visible to me or not. If it's not visible to me, they look alike. If the integer is visible to me, then they don't look alike. You will see that in the next lecture. Okay, so I see them for now wearing a tag, 1, 2, all the way to n, and there are markings on the floor. There is a mark 1, mark 2, all the way to mark n. Okay, the mark is the outcome of the experiment. Okay, so experiment 1 is who will occupy the first place. Okay, first place, let's say one possible arrangement is first place occupied by person 1, second place occupied by person 2, and place by person n. Okay, but of course the first place can be occupied by any person. Okay, so what happens here truly? If you think about it, first place is occupied by any one of the n individuals. Yes, so the number that can appear here is 1 through n. So first experiment has n possibilities. Good. Now, once this experiment is determined, the second experiment will always have n-1 possibility. So for example, if the outcome is person 1 is standing here, in the second place, persons 2 through person n can stand there. If this is person 2, then here you would have person 1 or person 3 all the way to person n, right? Regardless of what's the outcome in this box, the second box has exactly n-1 outcomes. Do you see that, guys? So what happens? It's n times n-1. The next box will be n-2. The next box n-1, and very last box, since all of them are already occupied, the very last box is occupied by only one individual. So it's already determined. So we have by the generalized principle of counting, this is n times n-1 times n-2 all the way to 1. So that is n factorial. Are you with me? So here is the next question, if you are with me. It's with numbers, and it has two parts, and I want you to construct a protocol. So we have a class, and the class has 6 men and 4 women. And in this class, the students will be ranked according to their performance. So the first part of the question is how many different rankings are possible? Okay, that's for all the students together, how many different rankings are possible. And part B is how many rankings if the men are ranked as a separate category from women, right? So, so best men and best women, they are not comparable, how good they are. I want not only the answer, guys, I want a protocol. I want a document by which you demonstrate why is this calculation that you're making correct. Good, guys, a few of you are ready. 1 second. Be very careful, guys, right? How you, so here we have, altogether 10 individuals. How many rankings of the 10 individuals? Assuming that no two individuals can occupy the same rank. Understand? So that's question A. Question A is very simple. Question B, slightly more difficult, very slightly. I think you are ready. Yes, guys, it's a simple question. You are ready. Yeah. Am I correct to presume that? So yeah. I want you to construct a Kafka protocol, even starting here, get into a habit. So the first Kafka protocol will be a bar consisting of of 10 boxes. Yes, of 10 boxes. And how many possibilities are there to fill box 1? 10 possibilities, right? Box 2, once box 1 is filled, 9 possibilities. And onwards until once I get to the last box, there is only one integer I can input into it. So that means it's 10 factorial, okay? So I think of codes, you see, I think of codes, and then the codes will right away tell me what happened. So let's say if the code happened to be, this is a correct input, right? 3, 2, 1, 4, 5, 6, 7, 8, 9, 10. This means that person number 3, person that has the integer 3 is the best student. Person that has the integer 2 is the second best, and onwards, okay? Those codes are the correct inputs. Do you understand the idea, guys? You associate a code. If you can look at the code and you can picture what happened, you can translate the code and see the students. And if you see the students and you can translate them into a code, that means you just have to count the codes. You understand? One-to-one correspondence. We'll see how you understand it, guys. Good. So there are 10 factorial possibilities. Are you ready with B? By the way, guys, I'm sorry if I scream. I'm not sure how it comes through the microphone. Very difficult to modulate my voice. Am I speaking too loud or?
You're
good?
Fine.
Good, thank you. Okay, so for experiment B, I want you to tell me what is the protocol, what documentation is going to be presented to describe the situation.
Would you just have 2 of those bar thingies from like one from 1 to 6, another one from 1 to 4, and then you have 6 factorial plus 4 factorial, and that would
would
be you would multiply it.
Oh yeah, multiply.
Multiply. And you see, what's the point of the boxes? The point of the boxes is the box is the experiment. Understand? Each box in your protocol is the experiment. You understand what we're doing? Why do you do the boxes? It's because every question, even very difficult question, will refer to this. You understand? So those boxes, experiment 1, experiment 2, experiment 3, how many possibilities for this? How many possibilities for this? You then multiply. And you have to understand, not just because I told you to multiply, you have to understand why I multiply and not add. Do I understand, guys, why I multiply and not add? Or do I need to explain again? Okay, let's wait. If you don't, I will explain again. it's extremely important at this very early stage to have a strong grasp. Otherwise, you will be terrified of what I'm gonna bring your way. I promise. Don't be bored. You will miss it. Okay. Where are we? We are. Yeah, here. Good.
Someone's asking to explain.
Why to multiply? Shut up. You guys, would you not mind if I go back and explain again? Yes. Thank you, Alejandro, for. I'm sorry, guys. You see, I spoke German more than I spoke any other language. I'm almost about to switch. You see, you left me alone. You know, I am so isolated, so socially distanced that I speak with Germans more than I speak with people that live next to me for those 3 months, or 3 hours a day almost sometimes, right? So yes. So here is the original situation. Okay, experiment. Think of just 2 experiments. Why do I multiply? Okay, so look at the situation. So we have one experiment represents just one set of outcomes, one input, one box. Okay, so with this coin, remember we have either heads or tails, heads or tails. Good. And now if I have 2 experiments, now I throw a coin, that's one experiment, and I toss a die, that's another experiment. Now we have 2 boxes. The first box represents the result of the coin. The second box represents the die. Do you understand? So, in that case, look what happened here. In that case, how many possibilities are there? There are 2 possibilities for the coin and 6 possibilities for the die. Look at it, 2 and 6. 2 times 6 is 12, right? So this experiment has 2 possibilities. Second experiment has 6 possibilities. 2 times 6 is 12. Now, how do you know that's the situation? You can list the first row to be where there is one particular outcome, let's say head in experiment 1, and then consider all the other possibilities for experiment 2, right? The experiment 2 is independent of experiment 1, which means that if H came out, I will have 6 possibilities. And if tail came out, I have 6 possibilities. That's very important. Otherwise, this property will not work, okay? If depending on the outcome of experiment 1, I have varying possibilities for experiment 2, this basic principle of counting does not apply. Good. So in general, so look what happened here. So it's 6 plus 6. So it's 6 added the number of times that there are outcomes for experiment 1. So what would happen in general if I have experiment 1 and experiment 2? If I get 1, if I get an outcome number, so then outcomes 1, 2, 3, 4, all the way to some number. If you don't like M, think this number is 10. And if you don't like N, think this number is 15. Okay. So for let's say this is again 10 and this is 15. So if 1 came out, I have 15 possibilities with 1 coming out. Yes. If 2 came out, I have also 15 possibilities. If 3 came out, also 15 possibilities. So I have 15 plus 15 plus 15. How many times? This number of times. Understand? 10 times. So it's 15 once, 15 twice, 15 3 times, all the way to 15 10 times. So it's 15 times 10. Times is just multiplication is just a way to count. Good. So it's M times N in general. So this is Y. You see why? So I'm just adding N plus N plus N. How many times am I adding N plus N? M N times. N times, right? So it's 1, 2, so N, 2N, Mn. Good. I think we'll begin with lecture 2 and we'll see, guys, if you think you know it, if you think you are, if you think to raise a nose. So, yes. So here is my Kafka document. And the Kafka document will remind me, so here are my men and here are my women. The Kafka document will remind me to multiply the number of outcomes of this experiment times the number of outcomes in this experiment. I apply the basic principle of counting. So how many possibilities are to rank men by themselves? The men by themselves are labeled with integers 1 through 6. There are 6 men, yes? So there are 6 factorial, thank you. And the women, 4 factorial. Understand? For every ranking of men, the women can be ranked independently, right? Because it doesn't affect how the women are ranked. That's the assumption here. So the answer is 6 factorial here, 6 factorial codes to write here, and 4 factorial codes to write here. This means 6 factorial times 4 factorial. That's my answer. You understand, guys? So you will have to overcome this idea that you have to see what you're counting. You have to develop tools where you know that what you counted is correct without being able to sieve through all the numerous possibilities. There are many. 6 factorial is already a huge number. Multiplied by 4 factorial, it's big. By the way, a small note to make. You see, obviously 6 factorial times 4 factorial is equal to 4 factorial times 6 factorial. But perhaps what this means is that the person that was doing this calculation had a different document from a person that was doing this calculation. You understand? Because in this document, men are listed to the left and women to the right. In this document, it might be the opposite way around, okay? That will help you think like this, okay? So when you are going to find some identities, countable, so some sort of combinatorial identities, you see one formula equal to another formula. And the reason is that both of them are documents that count the procedure correctly, but they do it in a different form. There are different forms that still will produce the correct count. Do you understand? So this is a very trivial case of it. That 6 factorial times 4 factorial equals 4 factorial times 6 factorial. I, in my head, already imagine a document where men and women are swapped. And here is already a slightly more challenging question, guys. Okay, let's see if you can do this one. And I want you to do it with a protocol. Okay, I mean, I want you to have this document. So you have, like I have there on my shelf, I have books, right? So you have 10 books that you wish to arrange. 4 of these books are math books. 3 of those books are chemistry, 2 are history, and 1 is a book about languages. You have to keep the category separate, you understand? So math books must be together. All math books are touching, all chemistry books are touching, or history books are touching, and onwards, right? But the order in which you list them is irrelevant, you understand? So you can put each category in any way which you like, and the books within the category can be moved. How many possible ways to arrange them on the shelf?
Professor?
Yes, please.
Did you say that the arrangement of the math, so like the individual math books, they matter? So if math books 1 through 4, like
yes. So regarding math books, you should all obtain the books by Stein and Shakarshi, right? So they are exactly 4 volumes. I can show you. They're on my shelf. So as you should have said 1 through 4. And you can arrange them 4, 3, 1, 3 to 1, or any other order.
And each of them will be a different possible.
Yes, each of them is a different possibility.
Okay.
So
Okay, so Erica, I see it's an interesting. Okay, so some of you guys I see wrote a mistake. One person actually answered it correctly. I'll wait a little longer and then I will explain.
So wait, do you want us to write it down?
Well, I mean, it's very difficult to write it down in a text, right? But I want you to do it for yourself at least.
Okay.
So I see a few of you are making a mistake. Okay, so so only one of the answers I see in the text is correct.
So Professor, there's going to be 5 categories, right?
Let's see how many categories. 1, 2, 3, 4. There are 4 categories.
Well, on top of that, there's also the restriction with so it would be, for me, I figured out it would be like 5 boxes or.
Sure. Well, if you figured it would be 5 boxes, perhaps you're thinking of it correctly. Okay.
Okay.
Yeah. So I'll explain to you how I think of it. Right. You have to.
Okay.
and I will try to get you to be comfortable with this idea. Okay.
All right.
Okay. When you're ready, guys, let me know. If you want to think about it, text, I want to think a little more. If you want to see the solution, let me know. And don't, guys, despair. It's already starting at this point. It's already becoming difficult. Okay. And it takes some ability to visualize exactly what is it that you have to look for. Lisa, okay, let's see, what did you say? Andrew, okay, already a few of you have, yes, okay, great. A few of you guys are seeing it, are seeing it the right way. Okay, so should we proceed? Great. I hope you are becoming slightly more excited. Some of your faces are so sad. So here is how I picture it, okay, more or less, right? So as I heard somebody was mentioning, I cannot see who it was. I had 5 boxes, okay? Here is what you have to understand, guys. How do you know that your coding, your Kafka document, as I call it, is correct? This is how you know it, right? If you fill in the document properly and you get the code, you should be able to imagine what was the actual outcome. You understand? Reading the code should give you right away a view of what actually happened. You understand? Yeah, I send you a code and you should know exactly what I'm saying. And if anything I want to say in this particular constraint, I should be able to put into code. Okay, so let's see what can happen if I go through the shelf. So I assign categories, right? So I assign code 1, that means math. You see, so here is my category. Here is math, here is chemistry, here is history, and here is language. Okay, so math is assigned category number 1. Chemistry is assigned category number 2, history category number 3, languages category number 4. You understand? So now imagine here, I walk through the shelf. You can decide if you want to walk right to left or left to right, but you have to decide, and it has to be kind of already informed, right? As you walk right to left, you are going to encode as follows. You are first going to note which are the categories, which categories I see. So as I move from one side to another, as I move left to right, what's going to be the first category I see, what's going to be the second category I see, third, fourth, okay? And then within math, right, how am I going to see the category math? Once I see math, what will I see, right? Which is the leftmost book, which is the next book, and onwards. In history, imagine those are volumes. They're by the same author, or you assign them a digit, doesn't matter, right? You understand? So you see that those books are labeled. Good? Completely with me, guys? Okay, so here is, for example, okay, guys, let's see if you can understand. Here I'm sending you this code. Okay, this is let's check if this is a properly completed code. So I go through here. What does it mean, right? It means what am I seeing? I first see category 2, which means when I move, I begin to see chemistry. Okay, I first see chemistry. And then what is the ordering of the chemistry books that I see? So I can look at this code this way. I can see this 2, chemistry, and then chemistry is this category, okay? So chemistry I see ordered correctly from volume 1 to volume 3, you see? So first on the shelf, leftmost on the shelf is chemistry. And this is correct ordering of chemistry, yes? Good. And then the next category I see is for language. So language, obviously, there's only one way to order it. It's just one book, right? Next, I see mathematics. And mathematics here is the ordering. It's also ordered properly, okay? And then I see 3. 3 is the last category that I see is history. And history is also ordered correctly. Understand? So this pattern indicates that the 1, 2, 3, 4, 1, 2, 3, 1, 2, 1 means that I decided to order the volumes in increasing order, from smaller to larger, all of them. Yes? And this tells you how do you notice the categories. You see, using this information, you can completely reconstruct how the books are standing on my shelf. Do you all see that? It's very important, guys. I want you to all be sure that you see that using this code, I can reconstruct how the books are on my shelf. I can see the books. If I strain myself, I can see exactly where they are. Is this true? Do you see it? Shake your head like this, that you do. Good, excellent. And don't be shy, guys. I will explain again and again. If something isn't clear, we will get it clear. Good. And yeah, so you understand this code will definitely translate to the actual shelf. I can see it. And actual shelf, I can translate it into this code. You understand? How do I do that? I first walk, I notice the categories, I write down the categories. Then each category, I focus on each category separately, and I tell you in which order that category is placed. You understand? So each particular shelf ordering will translate to a code like this, which means there is a one-to-one match with codes in my categories. Which means all I have to do is count the boxes. And you understand, in this form, notice many of you made mistakes. Not all of you. This question is already a few of you are pretty good at it. Maybe you have good instincts. But I would say from most of the answers that I've seen, there was at least a small mistake. You will eventually not have to write this, but I want you to always have this in your mind. Understand? Because if you do not have this in mind, you are not certain that you haven't made a mistake. Okay? So those are the experiments. So it's 4 factorial times 4 factorial times 3 factorial times 2 factorial times 1 factorial. You understand? Because what I did, I explicitly broke it down into the generalized principle of counting. Yes? You see, something happened to this thing. Whenever a person spoke, the person jumped in front, and now it doesn't happen. So I have to scan through all of you and hope that I can see you. Okay, we can move on, yes? Yes, so good, wonderful. So the answer was, as a few of you correctly wrote, is 4 factorial, 4 factorial, 3 factorial, 2 factorial, 1 factorial. And how do you know? Because that corresponds to this code. Okay, those are the experiments. Okay, and we finished the basic principle of counting. We go to lecture number 2. And now I will confuse you. Okay. Can you see what's on my screen, guys? Yes? So the next part is, how do we deal with overcounting? Thank you, guys. So you can see it. Thank you for reacting to me. Okay. Next problem is, how do I deal with overcounting? Sometimes counting directly is going to be rather complex. Okay. So here is the problem. We have 2 white pawns and 1 black pawn. Okay. And pawns that are of the same color are indistinguishable. I cannot tell them apart. You understand? This pawn and that pawn look exactly the same to me. Okay. How many linear orderings are possible? And by linear orderings, it's like with that photograph. I imagine I put the pawns in a row, and on the row I have markings. This is marking number 1, marking number 2, and marking number 3. And yes, and I just notice which pattern I obtain. And the pattern that I can notice is, in this case, it's white, white, black. Okay. If I take this pawn and that pawn and I rearrange, I don't see any difference. I cannot tell them apart. Okay. And here is again where it will come in handy to, later you will see why, to remember that even if the objects look alike and I don't distinguish between them, because they are 2 objects that at the same time occupy 2 different points of space, they are distinct objects. Okay. Even if I cannot tell them apart, they are distinct objects. So let's see, how do we carry out this calculation? It's a very simple problem. How many possibilities are available? I can do it directly by listing those possibilities. You agree? Because the pattern is distinguished by the position of the black pawn. Because so it's either white, white, black. So black is last, or black is middle, or black is first. And those are the only possibilities, 3 possibilities, yes? So for this problem, I specifically made it very simple so that you can do it in 2 ways, because doing it like this, listing out the possibilities, will end up impractical. It will be too difficult, okay? So there are 3 possibilities. The patterns are those 3 patterns, yes? So what we have to do now, and this is what, again, I have the same problem with students as I mentioned, right, is I'm going to try to make those pawns distinguishable. And what do? In my head, I imagine that the pawns have swallowed an integer. So this pawn swallowed 1, this pawn swallowed 2, and this pawn swallowed 3, okay? So although I cannot see the difference is there, okay? So if I see the difference, this number comes in front, and if I can't see the difference, this number is in the belly. Good. So here I will start. I can try to create a protocol by which I list them as individuals. Right? How many possibilities are there to list them as individuals? And the protocol is clearly first place, second place, third place, and that's permutations. You agree? So in the permutations, what do we have? We can have the pattern 1, 2, 3. So you see, there are going to be 3 factorial possibilities, right? So 3 possibilities for which pawn goes here, 3 possibilities for which pawn goes here, and 3 possibilities for which pawn goes here. But not all of those possibilities are different. You understand? So I have a code that is too robust. It has too many synonyms. Do you understand what I mean by synonyms? Basically, suppose that I want to encode the possibility white, white, black. Using my coding system, there are synonyms, right? I have the code 1, 2, 3, and the code 2, 1, 3. Do you agree? 1, 2, 3 means white, white, black. 2, 1, 3 also means white, white, black. And since that's all I can tell, those 2 documents are not describing a different outcome. They're describing the same outcome. You see, I have a code. It's a nice code, but it's overcounting. You understand? I produce too many codes for the same situation. I have enough codes to account for all possibilities, but I have synonyms. I have several codes that describe exactly the same situation. Interrupt me, guys, if something is unclear. It's very, very important that you get what I'm trying to get, okay? So what do? I do something that's called stapling. In topology, it's called quotient topology if you studied it. Or you can think simply that I'm stapling 2 documents together, and I consider the pile of those documents to mean an individual outcome. Yes? The pile of those documents is my individual outcome. So there are 3 factorial documents. Think about it very carefully, right? And those documents can be broken into exactly 3 piles. This is the pile corresponding to the outcome white, white, black. White, black, white, 2 documents, and black, white, white, also 2 documents. You understand? You're with me? So look at it. All those documents, this is a pile. I just drew it separate, but you can imagine we staple one onto another, right? So we have 1 pile, 2nd pile, 3rd pile. Instead of the actual code, the pile containing all synonyms stands for the individual outcome. That's how I avoid overcounting, you see? And I'm going to explain what I do then, right? So what do? I know that 3 factorial equal to the number of piles multiplied by the number of documents in each pile. Again, the assumption is that each pile has the same number of documents. Do you see that? So my number of unique outcomes is given this way. Number of piles multiplied by number of codes per pile, or number of documents per pile, equal to total number of documents. And that works only if each pile has the same number of documents. Then to count the number of distinct possibilities, I just have to count the number of piles. And what do? I take the number of documents and divide by the number contained within each pile. Look at it. It worked here, correct? So look at it. This is 6. 6 divided by 2 will give you 3, just like we had over here, 3. 6 over 2 is 3. You understand why, right? So those 2 documents, this is 1 pile. They correspond to the same outcome. another outcome contains 2 documents, another outcome contains 2 documents. So the number of piles will be the number of unique patterns that I can distinguish. Good? And each pile contains the same number of documents. So if I know the number or if I know the total number of documents and I know the number within the pile, all I have to do to figure out the number of piles is to divide the total number of documents by the number within each pile. Are you with me, guys? Good. It is very, very important to understand it, okay? Let's see if we can do this. I will give you an opportunity to do it on your own, and then I will actually do it in 2 ways, right? I will do it. One of the ways might even confuse you, but I think it's an important way to do it, right? I want you to understand very abstractly because you're not going to be able to count directly, right? So imagine this is what you have. You have 6 pawns. 2 of them are white, 1 of them is black, and 3 of them are red, okay? How many distinguishable linear patterns are possible? You understand by that? I mean, I can tell white, white, black, red, red, red. That's what's to me distinguishable, right? But everything that's red, if I interchange 4 and 5, I can't tell it. Okay. So the total number of very, very careful. Yeah, so what I want is the total number of patterns, right? What you wrote is possibly useful for the problem, but that's not what I need. Alejandro. Yes, Erica, you are correct. We will do it again in 2 ways, right? So you might already see why that's the answer, or you know, I want you to be able to present your answer in terms of the documentation. Okay? I want it to be like the Kafka document or a Kafka protocol. Let me know when you're ready.
Okay, I see what I did wrong. I'm ready.
And who is speaking to me?
Alejandro.
Ah, thank you, Alejandro. All right, guys. So let's go over it. And okay, so this is what I think. So my first Kafka form will be to regard each pawn as an individual. So what I imagine is that each pawn has a number in its belly, and I wrote the number actually below. Okay, so the numbers are 1 through 6. Okay, so 1 and 2 represent the white pawns, 3 represent the black pawns, and 4 through 6 represent the red pawns. Yes. So if they are all distinct individuals, there are clearly 6 factorial possible ways to fill in this form. Okay, but as you obviously see, there are redundancies, right? Because let's say if I have the code 1 2 3 4 5 6 or the code 1 2 3 5 4 6, they represent the same pattern because all I see is white white black red red red. Yes. So just 6 factorial, it's capturing all the outcomes, but it's redundant. Understand? It's overcounting. So what do I do? Right. So the pattern that we observed here is WWBRRR. That's the pattern I wrote over here first, right? How many codes will correspond to this particular pattern? In other words, how many synonyms are there, right, for this pattern? And then I will staple them to make the synonyms just one word. That's the idea, okay? So I will first do it intuitively without a form, right? So look at it. This is the pattern, right? This is the pattern. I can interchange the whites among themselves without any change, so there are 2 factorial. 3 I can interchange with itself, so there is 1 factorial. And those I can interchange among themselves, so it's another 3 factorial, right? So how many synonyms for this particular pattern? 2 factorial times 1 factorial times 3 factorial, okay? That means, I will do it again. If you don't understand it by this hand wavy approach, I will try to explain that very precisely later, okay? If you look at it, the pattern white, white, black, red, 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 it repeats 2 factorial times 1 factorial times 3 factorial in 2 factorial times 1 factorial times 3 factorial documents in here, okay? And that will be clearly true no matter how I interchange the patterns. So for every other pattern, will repeat exactly the same number of times. What does it tell me? It tells me that each particular pattern has, I call it a word, right? So this is 1 through 6 is a word. So 1, 2, 3, 4, 5, 6 is a word that represents this pattern. Understand? How many words to represent this pattern? 2 factorial, 1 factorial, 3 factorial. For every other pattern, there will be also 2 factorial, 1 factorial, 3 factorial words, which means now I have piles. Each pile is a synonym. Another pile, it's a different pattern. Another pile, a different pattern. I do not know how many piles I have. Yes, I don't know how many piles I have. So the number of piles is k. But what do I know? Multiply the number of piles by the number of documents in each pile, and I get 6 factorial. You follow me, guys? So what happens because of that? I get 6 factorial divided by 2 factorial, 1 factorial, 3 factorial. That is total number of documents divided by number of documents in each pile. Within one pile, how many documents there are. That will give you the number of piles. Are you with me? Number of piles rather than the document is now a representation of a pattern. Okay? So there are, in this case, what? In this case, there are 12 documents. The pile is 12 documents thick that represent white, white, black, red, red, red. Okay? There are 12 documents in this pile. Any other arrangement, it will be a pile exactly of size 12. So I have this is one pattern, another pattern, another pattern. I have many piles. I don't want to count them, but I know that in each pile I have 12 documents, and I know that total number of documents is 6 factorial. Okay, so take total number of documents, divide by the number in one pile, and you get the count of the piles. You understand? I have a much more elaborate explanation about it, which I can do it now, or I can do it, starting from the next class. It might confuse you, but I think it's a good exercise. I want you to try to document everything or justify everything by a documentation. Then you will be better at this type of problem solving. So, by the look of you and by your silence, I think you had enough, correct? All right, so I will stop the video. Thank you that you laugh. Your laughter brings joy to my heart. And yeah, so what we do now is I'm going to stop the video. If you still want to talk to me about something, you are welcome to do so. Okay.
Professor,